Hardware forms the physical foundation of every business operation. From computers and servers to networking devices, hardware powers the tools and infrastructure that businesses rely on to store data, run applications, and connect teams across the globe. This is Chapter 2 of a larger course titled Introduction to Information Technology. And besides an introduction itself, the overall course is designed to bridge the gap between technical IT concepts and their practical application in business operations. In this chapter, we will examine the critical hardware systems that support business operations. We will begin with the basics by understanding what a computer system is and how it functions, starting with the IPOS cycle. Next, we will deep dive into the internal components of a computer system, covering key parts such as the motherboard, CPU, RAM, and storage. We will then explore the external devices and interfaces, including input-output devices and connection methods. We will also discuss specialized components such as network interface cards and graphics processing units. Now that we have a clear understanding of the key components, we will look at how these elements interact to perform meaningful tasks. This includes an introduction to Neumann Architecture and the role of memory in processing. Servers are widely used in business environments where there are multiple users and high workloads. We will explore the key differences between servers and personal computers. Today's IT infrastructure extends beyond physical devices. In this section, we will learn about the alternatives such as cloud computing and virtualization. Finally, we will wrap up with a practical exercise where we analyze the hardware specifications of a high-performance laptop to understand the real-world application of what we have just learned. By the end of this course, you will understand the operational mechanisms of your IT infrastructure and its impact on business functions. A computer system is a collection of interconnected devices that help handle tasks, process data, and support workflows. It is made up of two key parts: hardware and software. Hardware refers to the physical components of a computer, like the CPU, RAM, and storage devices. Software provides the instructions that tell the hardware what to do, such as running applications or executing programs. There are various examples of computer systems. Laptops and desktops are commonly used for business tasks like emails and presentations. Servers are more powerful systems that store data, run applications, and support multiple users. Smartphones and tablets are portable devices used for both personal and business tasks. Embedded systems are computer systems designed for a specific function within a larger device. An example in personal use would be a washing machine's control system. Internet of Things or IoT devices are embedded systems with network connectivity, allowing them to communicate with other devices and the internet. Examples would be smart security cameras and wearable fitness trackers. All computer systems follow the IPOS cycle, which stands for input, processing, output, and storage. Let's break it down. Input is the first step where data enters the system. This can be as simple as typing on a keyboard, clicking on a mouse, or even speaking into a microphone. Processing happens when the computer's processor takes the input data and performs tasks based on the instructions provided by the software. For example, performing calculations in a spreadsheet or editing a document. Output is when the computer produces meaningful results from the processed data. A common example is displaying a document on the monitor or providing an audio response if it's a voice assistant. Storage is where the computer saves the data and instructions for future use. For example, when you save a document on your hard drive or cloud storage. These four steps work together to allow a computer to perform tasks and provide the results you need. Now, let's explore the hardware inside a computer that makes all of this possible. First, we have the motherboard. This is the main circuit board where all the essential components sit. These components are connected via pathways called buses. The central processing unit or CPU is the core processing unit executing instructions and performing calculations. Clock speed, measured in hertz, indicates the rate at which the CPU can process instructions. A higher clock speed generally translates to faster processing. Core count refers to the number of independent processing units within the CPU. More cores help with true parallel execution, improving performance in tasks like data processing, virtualization, and AI. So for example, a quad core or 4-core CPU can handle 4 separate tasks at the same time, like working on a presentation in the foreground while email syncing, a cloud backup, and a data analysis tool running in the background. A thread is an individual sequence of instructions that a core can execute. Multi-threading allows a single core to handle multiple threads by switching between them quickly. So for example, a 4-core CPU with 2 threads per core appears as 8 logical processors, improving multitasking and workloads like database queries. Memory primarily refers to RAM or random access memory, which serves as a temporary or volatile storage for active data and programs, providing fast access for the CPU. RAM capacity, measured in gigabytes, directly impacts the ability to handle larger data sets, run multiple applications simultaneously, and perform memory-intensive tasks. If you're working with large spreadsheets, databases, or complex software, adequate RAM is essential for smooth operation. Storage devices provide persistent or non-volatile data retention. That is, data will exist even when the system is powered off. HDDs or hard disk drives use mechanical platters to store data, offering higher capacity at lower cost but with slower read-write speeds. SSDs or solid-state drives utilize flash memory for data storage, providing significantly faster access times, improving application load times, system responsiveness, and overall user experience. SSDs are more expensive than HDDs. Next, let's look at the hardware that connects from the outside of the computer casing. These devices enable user interactions with the computer system. Input devices such as keyboards, mouse, scanners, microphones provide data input. Output devices like monitors, printers, speakers, and projectors present processed information to the user. These input-output or I/O devices can connect via wired or wireless connection. In the case of wired connections, ports provide connection points for external devices, expanding the system's functionality. Universal Service Bus ports or USB ports connect a wide range of peripherals, which include keyboards, mice, external devices, and flash drives. The most common USB ports are Type-C and Type-A. And just to be clear, the port is the top portion of the picture on the screen, which is found on the side of the computer. And the picture below it is the cable that connects onto each specific port. High-definition multimedia interface ports or HDMI ports connect display devices like monitors and projectors. Ethernet ports allow a wired network connection for stable internet access. The Ethernet port is also called an RJ45 port. Audio jacks connect speakers, microphones, and headsets. Some external devices can connect wirelessly, that is without cables, requiring built-in or external adapters. Bluetooth enables wireless connection for keyboards, mice, headphones, and speakers. It requires a Bluetooth adapter, which can be built in or as a USB dongle. Wi-Fi is commonly used for wireless printers, smart devices, computers, and many other gadgets. It requires a Wi-Fi adapter either built in or through USB. And then we have RF or radio frequency. Many wireless peripherals use radio waves to communicate with the receiver plugged into your computer, often via USB. Network connectivity is essential for modern business operations, enabling communication, data sharing, and access to remote resources. A network interface card or NIC is a hardware component that connects a computer to a network, allowing it to access the internet and communicate with other devices. NICs can be wired or wireless and are critical for both personal and enterprise systems. A graphics processing unit or GPU is a specialized processor optimized for handling complex computations, particularly those required for rendering images, videos, and 3D graphics. Originally designed for gaming and visual processing, GPUs have evolved into powerful parallel processors used in various business and technical applications, including data analytics, AI model training, scientific computing, and financial modeling. Their architecture enables the simultaneous processing of large data sets, making them highly efficient for tasks that require massive parallel computation. Okay, so far we've looked at what the major components within a computer system are. Next, let's look at how these components are designed to work with each other. To make a computer perform meaningful operations, we need to communicate with its CPU through instructions. So what is an instruction? An instruction is a basic command that tells the CPU to perform a specific operation, such as performing arithmetic, transferring data, or making comparisons. Instructions are typically written in binary, which is machine language, so that the CPU can understand them directly. But for human readability, these instructions are often represented in assembly language. Each instruction consists of two key parts. First is the opcode, which is the operation code that tells the CPU what action to perform. And we have operand, which is the data involved or the memory location of where the data can be found. So for example, add AB tells the computer to add the values stored at memory locations A and B. Here add is the opcode and AB are the operands. Another instruction would be load X, which retrieves the value stored in the memory location X. And we could also have store Y, which saves the results of an operation to the memory location Y. An instruction set is the complete collection of all the instructions a CPU can execute. Each type of CPU has its own specific instruction set defined by its instruction set architecture or ISA. The ISA is a blueprint that defines how a CPU works and how it communicates with memory and external devices. It dictates how the CPU can handle data and instructions. Examples of ISAs would be x86, which is used in desktop and laptop computers. And we also have ARM, which is found in many mobile devices and embedded systems. Some instructions in the x86 ISA include MOV, which is the instruction to move data from one location to another. We have ADD, which adds two values, CMP, which can compare two values, and JMP to jump to another instruction, which can be used in loops and branching. Now that we understand instructions, let's explore how computers are structured to process them. The von Neumann architecture is the most common design for computers. It is based on the stored program concept, meaning that both data and instructions are stored in the same memory. This allows the CPU to access them both easily, enabling efficient processing. So the CPU is the brain of the computer responsible for executing instructions. It consists of the control unit, which directs the operations of the CPU, fetching instructions from the memory and coordinating their execution. The arithmetic logic unit or ALU performs arithmetic and logical operations such as addition, subtraction, and comparisons. Registers are small high-speed storage locations within the CPU that hold data and instructions being actively processed. Registers are faster than RAM, reducing the time the CPU waits for data. Memory or RAM acts as temporary storage, providing quick access to data and instructions. Think of RAM as a filing cabinet where the CPU stores active tasks. Each piece of data or instruction in RAM has a unique address, enabling the CPU to retrieve it efficiently. The communication between the CPU and other components like memory is handled via a collection of wires called the system bus. The system bus consists of data bus, which carries the actual data being transferred, address bus, which carries the memory address where the data should be read from or written to. Control bus carries control signals from the CPU to manage other components. And finally, we have the input-output or I/O devices. As seen previously, input devices, for example, keyboard, mice, allow users to send data and instructions to the computer, and output devices like monitors and printers display the results of the computer's processing. Now, let's see how the CPU processes instructions step by step in a cycle called the Fetch-Decode-Execute cycle. The first step is fetch. So first the CPU retrieves an instruction from the memory. Then is decode. The CPU decodes the instruction to understand what action needs to be taken. And then we have execute, where the CPU performs the operation, for example, some calculation or data movement. And then repeat. The cycle repeats with the next instruction. This cycle happens billions of times per second, enabling the computer to process instructions and respond to user input seamlessly. Now let's check out the role of memory in helping the CPU process instructions. So when we run an application like Microsoft Excel on our computer, the program file excel.exe is loaded from the storage device or hard disk into RAM because RAM is much faster. The CPU then begins the fetch stage of the cycle, retrieving the instructions from the RAM. As the application is running, the CPU will refer to cache memory first before reaching out to RAM. Cache is a smaller, faster memory located closer to the CPU than RAM. It stores frequently accessed data and instructions, anticipating the CPU's needs. When the CPU needs data, it first checks the cache. If the data is present, which is a cache hit, the CPU retrieves it quickly. If not, which is a cache miss, the CPU retrieves the data from RAM and a copy is placed in the cache for future access. Cache is organized into a hierarchy with levels like L1, L2, and L3. L1 is the smallest and fastest located closest to the CPU, while L3 is larger and slightly slower. So, whether retrieved from the cache or RAM, the current instruction that is being actively executed gets stored in the registers, which are the fastest memory locations inside the CPU. Once the task is completed or when the application is closed, the temporary data in RAM is either cleared or replaced with another application which requires memory. The operating system of the computer handles this memory management. We will learn more about operating system in the next chapter on software. So far, we've encountered different types of memory, each with different characteristics and different roles to play. The memory hierarchy is a structure that organizes these different types of memory based on speed, size, and cost. Faster memory is closer to the CPU, but it is typically smaller and more expensive, while slower memory is larger and cheaper. Let's explore the levels. Registers are the fastest and smallest and are located in the CPU. Cache memory L1, L2, L3 is faster than RAM and stores frequently accessed data. RAM is the primary working memory for active tasks. Virtual memory is an interesting one. When RAM is full, a portion of the computer's storage drive, which is the HDD or SSD, is used as an extension of RAM, allowing the system to run more applications or handle larger data sets than physical RAM alone would permit. This is called virtual memory. And HDD or SSD storage is the slowest in speed and the largest in capacity. Now let's move on to a topic which is very relevant in a corporate environment: servers. While personal computers handle individual tasks, businesses need machines that can serve multiple users at once. These machines are called servers. Common uses of servers in a business are file servers, which store and manage company files, database servers, which run database applications like Microsoft SQL Server, Oracle, or MySQL, web servers, which host websites and online applications, application servers, which run enterprise software such as ERP or CRM systems. Many businesses now use remote servers, often referred to as cloud computing, to reduce costs and improve flexibility. While both servers and PCs may seem similar on the surface, servers are much more powerful than PCs. Let's look at 4 key differences. First is performance and processing power. Servers are equipped with high-performance, multi-core CPUs designed for intensive workloads. These processors excel in parallel processing, making them ideal for tasks such as data processing, virtualization, and large-scale computations. PCs, on the other hand, use consumer-grade CPUs optimized for general-purpose performance. They are not built for sustained heavy workloads or large-scale data processing. Then is memory and multitasking. Servers have large amounts of RAM, for example 128 GB, 256 GB or more, which is error correcting or ECC RAM, which prevents data corruption. This helps in running multiple services reliably without crashing. Then is storage and redundancy. Servers use specialized storage known as RAID, which stands for Redundant Array of Independent Disks, to prevent data loss. RAID ensures that even if one hard drive fails, the system continues running without downtime. This is also referred to as fault tolerance. And we have concurrency and multi-user support. Servers are built to handle multiple users simultaneously, whereas PCs are designed for one user at a time. Managing hardware effectively presents several challenges. Hardware technology evolves rapidly, leading to frequent obsolescence. This necessitates regular upgrades and replacements, incurring significant costs. Purchasing, maintaining, and upgrading hardware can be expensive, especially for large organizations with complex IT infrastructures. Managing diverse hardware components, ensuring compatibility, and troubleshooting issues requires specialized expertise. Hardware vulnerabilities can be exploited by malicious actors, compromising sensitive data and systems. Traditional hardware infrastructure can be difficult to scale quickly to meet changing business needs. Several alternatives can mitigate these challenges. Migrating to cloud-based services reduces the need for on-premise hardware, shifting the burden of hardware management to the cloud provider. This offers cost savings, scalability, and increased flexibility. Virtualizations allow multiple virtual machines to run on a single physical server, maximizing hardware utilization and reducing the number of physical servers required. This lowers costs and simplifies management. We'll deep dive into both these technologies in Chapter 6 of this course. To wrap up this chapter on hardware, let's look at the specifications of a high-end laptop. We'll be focusing on a Dell XPS model known for its powerful performance. We will dive into the details of the processor and memory specifications to understand how they impact performance. Let's go through each specification one by one, and note that this exercise is only for educational purpose. Let's start with a breakdown of the CPU specs. The first line, Intel Core Ultra 9185H, indicates the specific model of the CPU. It details the processor's brand, family, tier, and specific model number. The core count refers to the number of independent processing units inside the CPU. This particular processor has 16 cores, which is a high number for modern laptops. These are split into 6 performance cores or P cores, which are optimized for high demand tasks like gaming, video editing, and 3D rendering. Then we have 8 efficient cores or E cores and 2 low power efficient cores. These cores handle less demanding background tasks while conserving battery life. Thread count refers to the simultaneous tasks or threads that the CPU can manage at once. Only P cores can handle 2 tasks at the same time or dual threading, which is the Intel hyper-threading technology. So, 6 performance cores times 2 threads gives us 12 threads. Combined with the 10 efficient cores, the CPU can handle 22 threads in total. The cache acts like a quick access notepad for the CPU. This particular CPU has a 24 MB cache, which is likely L3 cache, which is used for fast access to critical data during heavy processing tasks. Clock speed, which is measured in gigahertz, indicates how many cycles a CPU can complete in 1 second. 5.10 gigahertz means that this processor can perform 5.1 billion operations per second. It also features turbo boost. The CPU can temporarily increase its speed during demanding tasks such as video rendering or gaming. However, know that the clock speed on efficient cores is typically lower than on the performance cores. Now let's break down the memory specs. The amount and speed of RAM directly impacts a computer's performance. More RAM allows a computer to handle more tasks simultaneously and run larger programs without slowing it down. This laptop comes with 32 gigs of RAM, which is excellent for multitasking and handling resource-heavy applications. Let's do a quick breakdown of the amount of RAM offered in modern personal laptops today. 4 gigs is the bare minimum required for light tasks such as basic web browsing, document editing, but expect noticeable slowdowns with even the most moderate of multitasking. 8 gigs is sufficient for most day-to-day tasks and moderate multitasking. But still, demanding applications or heavy multitasking can strain this amount. 16 gigs is ideal for gamers, content creators, and heavy multitasking. It provides a smooth experience for most modern applications and games. 32 gigs would be required for professional video editing, 3D rendering, virtualization, and advanced simulations. This amount ensures smooth performance in resource-intensive tasks. As of today, 64 gigs is likely overkill for most general users. However, if you're involved in more demanding tasks like high-end video editing or large-scale data analysis, it can be beneficial. More importantly, keep an eye on this space for AI development. As AI models become larger and more complex, they will require significantly more RAM to operate efficiently. So we may see 64 gigs becoming the standard in future. So watch this space. It is also important to note that GPUs can complement and in some cases alleviate RAM limitations. Modern GPUs have their own dedicated memory or VRAM, which handles graphics-related tasks. But beyond graphics, GPUs are also crucial for artificial intelligence tasks, particularly deep learning. The GPU's ability to handle parallel computations and its dedicated memory mean that it can take on a significant portion of the processing burden, reducing the need for excess amounts of system RAM in certain scenarios. Let's move on to the next spec. LPDDR5X stands for Low Power Double Data Rate 5X. This is an advanced type of RAM that is more energy efficient, making it ideal for laptops that need to conserve battery while maintaining high performance. The 5 in DDR5 refers to the generation of the RAM. DDR5 provides significantly faster speeds and higher bandwidth compared to previous generations, improving overall performance. And a quick side note, bandwidth refers to the amount of data that can be transferred per second. A similar concept to bandwidth is data transfer rate, which measures how many data transfers the RAM can perform per second. And a transfer is a single data operation. So the 6400 MTS refers to the data transfer rate of RAM, meaning it can perform 6.4 billion data transfers per second. Higher data transfer rates enable quicker data retrieval, resulting in faster application loading, smoother performance in complex tasks, and better multitasking capabilities. And let's move on to the storage breakdown. This laptop features an SSD and not a traditional HDD, meaning that data access is inherently faster due to the absence of moving mechanical parts. The SSD has a storage capacity of 512 gigs. This refers to the total amount of data that the drive can hold, such as documents, photos, software, operating system files, and more. The M.2 form factor refers to the physical size and shape of the drive. M2 is a compact, space-efficient design, perfect for thin laptops. PCIe, or Peripheral Component Interconnect Express, is a high-speed interface that allows the storage drive to communicate quickly with the rest of the system. This significantly boosts performance compared to older storage interfaces. NVMe, or Non-Volatile Memory Express, is the protocol used to increase data transfer speed between the storage drive and the CPU. It performs faster read-write speeds, which means quicker boot times, faster file transfers, and overall better performance, especially in data-heavy applications like video editing and gaming. So let's summarize how these components work together in real-world tasks. The 16-core processor allows the laptop to handle the most demanding of applications and even less intensive tasks at the same time. The 22 threads enable smooth multitasking without slowdowns. The 32 gigs LPDDR5X RAM ensures that large files and complex applications run smoothly. The 6400 MTS transfer speed guarantees that data is retrieved quickly, so you won't experience delays when switching between applications or working with large data sets. The 512 gigs NVMe SSD allows for rapid data access, improving overall system responsiveness. However, for users who need large storage capacity for media or large files, an upgrade to a larger SSD or external storage should be considered. Alright, time to wrap up. We have examined the critical hardware elements that drive our IT systems. To summarize, hardware provides the infrastructure, while software directs it by sending instructions to perform tasks. Computers process data through a cycle of input, processing, output, and storage, which ensures efficient data flow. The CPU, RAM, and storage are essential for processing, storing, and managing data in a computer system. Buses, ports, and wireless connections enable communication between different components and external devices. NICs enable network connectivity, and GPUs handle graphics processing tasks. The von Neumann architecture is a design that allows computers to store both data and instructions in the same memory, facilitating instruction processing. Memory hierarchy optimizes system performance by using fast, small memory types closer to the CPU and slower, larger memory for long-term storage. Servers are designed for high-performance, multi-user tasks, while PCs are meant for individual user applications. Cloud computing and virtualization provide scalable and cost-effective alternatives to traditional hardware for businesses. And lastly, understanding hardware specifications is crucial for selecting the right components to meet specific performance and needs.